Okay, thanks. Yeah, so I'm gonna continue on with what Ted was describing yesterday, and so my goal today is to indicate for one why this height bound. So Ted sort of described there's this set of generators that comes from building this magic fundamental domain for an S unit group once you invert enough primes. And what I'd like to sort of describe is, well, one, a little bit about why that height is bounded. Why aren't this magic height that we define by all the 900 different norms we have? And but secondly, I want to focus in on an example, a very simple example of the Hamilton quaternions over Q, and show you that actually our height bounds are ridiculously computable. So it's not like we have this generalization of Lenstra's method of finding generators for S units of number fields. And okay, you generalize it, but if the constants are like d to the d to the d to the d, where d is the degree of the algebra, then this is perhaps a waste of time. But in fact, you can actually compute stuff, and this might lead to some interesting things you can actually compute. So today I'm going to focus in on a quaternion algebra over Q. I'm going to just sort of stick to that special case so that the formulas and everything become a little bit simpler. And so D is going to be a now integral order of B. We're going to take S, some finite set of places. It's going to contain the Archimedean place. And our goal is going to be to find generators of this of small height. And I'd like to recall what that height meant. This is all this technical stuff you have to do. But basically, what do you want to do? You want to realize your algebra at each place as matrices over some division algebra, over that local field. And then you want to sort of use the reduced norm of that local field. Now you want to look at the matrix entries. And your height's going to come from studying that. So this is what you get in that case. And so what's the point here? So you're going to take the reduced norm to the 1 over the degree in the Archimedean setting. And, for these algebras over the non-Archimedean local fields, you get this unique maximal ideal. You still get a uniformizing element. You can read up all about this in Bayes' book. And so you do get a formula for this in the Archimedean case that looks pretty familiar. You get the size of the residue field to the minus 1 over dv. And there should be a, yeah, that's right. That's right. So lambda v is this uniform. So technically what I said there is forget this. Okay, that's better. So now you have some power of this, and you get that it's a power of that number. Okay, sorry about that. So again, we want to study completion. So here we have a quaternion algebra over Q. So at the real place, we can say that it's either Hamilton's quaternions or it's going to be 2 by 2 matrices. And we need a notion of a measure on this. And so we're going to take, so considering Hamilton's quaternions as being this 4-dimensional vector space, we're going to take 4 times dx 1, 2, 3, 4 for reasons I'll explain in a second. So that we can think about the coordinates as coming from our favorite generators for this algebra. And on R, we're going to take just the regular one, and then we're going to pass to the product measure on R4. So now our order D is going to embed as a lattice, and its covolume is going to be the discriminant. And that's the whole reason that we pick this normalization for the Haar measures. And you can, once you start getting bored, if you want to work this out, it might be as boring as me though, this Haar measure comes from a trace definition just like the discriminant is. So the discriminant of an algebra, you can describe it as the absolute value of the determinant of a trace matrix where you've got generators. And so the reason we pick this measure is because it's born to win with respect to the discriminant. And our point is that we want to bound this height in terms of the discriminant, and sort of, the natural invariance of this order should give our height bound. So that's why we pick this measure. So now, you recall from what Ted said, is the first thing where our main strategy here is to use Minkowski. And Minkowski is going to return some element of D, and we want to show that that element's going to be in D star, and that's sort of the mechanism. So to use Minkowski, the first thing you want is a convex symmetric set, and that's what I'm going to try to define now. So we've got our norms on these algebras, and XC. So I'm going to pick a special convex symmetric set. So again, in our paper, we sort of take a generic convex symmetric set, and you can get all these bounds and stuff. But today, I want to focus in on a very particular one, which is a box. So nice convex symmetric set. And so the volume with respect to these metrics we're taking is going to be as you see there. So what's going on here? I'm saying that I'm taking, so what am I taking? In the Hamilton-Quaternion case, you notice I've got that power of dV, which comes up for sort of technical reasons. So the point is, you've got the square norm on R4, if BR is Hamilton's quaternions, and you've got just the regular norm on R4, if you've got 2x2 matrices. So you get that that's the volume with respect to our measures. And what do we want to do? So Minkowski says, I've got this lattice. Its covolume is the discriminant. And so I want my convex symmetric set to be sort of optimal. I want to hit it right on the nose. So I want the volume of X sub C to be 2 to the dimension over Q times that, so 16 times the discriminant. And so there you go, there's your C in each case. Okay? Explicit on the nose. Okay. And now, the point is, you want to do a little push and pull. So now you want to look at how the norms are bounded on this. The sort of Archimedean norms are bounded on this. And then you're going to define your fundamental domain using a sort of similar non-Archimedean bound back and forth. So I'm going to look at this constant. This will make a little more sense in a second. We'll look at this constant m sub x. So this funny norm is bounded. So I want to see how the norm is bounded on my convex symmetric set. And you can just compute it by hand. And you get that. And remember, we had this finite set of places. And then we defined this set f sub x sub c, which I should put the definition of G sub s as well. So G sub s was, right, we took the product of the R. So remember, S was supposed to contain all the Archimedean places. So that's good. And then we had the product of the completions over the finite places. And inside of G sub s, so because the product formula holds for the S unit group, we have a natural embedding of the S unit group into G sub s. And the claim is going to be that if S is sufficiently large, that this set, F sub xc, is a fundamental domain for that action, or a fundamental set. It contains a fundamental domain. It doesn't exactly tile. It's perhaps a little beefier than it needs to be. And so the condition is that at the Archimedean place, you're in my convex symmetric set. And then here's this push and pull I was saying. Now you want to look in the non-Archimedean side at things that map the order back to itself. Now recall when you have something that's not integral, right? You multiply and intersect to get the beta times d. And you want that norm to be bounded, the index rather, to be bounded by my norm bound. Right? So now I'm getting a non-Archimedean bound out of my Archimedean bound. And so that's a compact set now. And there's the proposition that needs to go up. So if S contains all the finite places where the norm squared is less than m sub x, then this is a fundamental domain. So once I throw in, so m sub x, we had is it still here? Where'd it go? I guess I lost it already. Oh, it's on this sheet. Yeah, right. So we have an explicit formula for m sub x. And so now we can explicitly say, okay, well, once I have inverted this many primes, I get a fundamental domain. And in the theory of algebraic groups, this has always been a big problem to sort of effectively create fundamental domains. It's actually quite hard. I mean, you learn the fundamental domain for the modular group when you're a small child reading your first number theory book. And, you know, it's just one of these things that you learn without having to really figure out the first time. But yeah, how do you come up with these things? That one's kind of natural. Maybe you could spend a few hours. But so this is actually a significant problem we're solving here, finding fundamental domains for action. And now I wanna first cover this up so I don't scare you too much. So the other ingredient we needed now to find these generators were these topological generators. I want to spend a page sort of yapping about those. So what was a topological generator set for this group OS? This product of BVs over the V's and S. Well, basically we want a set so that when we take the group generated by P, and any open set O, anyone, just pick your favorite one, and we're going to get the whole group. So I'm going to sort of generate this place by place. So in our case, this is not so bad to do. Okay, so let's assume that BR star is GL2R. Okay, GL2R has two connected components, and they're determined by the sign of the determinant. And so if you take an open subset, you take the subgroup that generates, that's going to contain an open neighborhood of the identity, and that's going to generate the whole connected component of the identity. Pretty much because, well, you now get a transitive action, and you've got the full dimension, so you've got everything in the connected component. So at worst, you need this element. Now I need to throw in some ones and make sure it satisfies the product formula, at least up to sign. And so in the Archimedean place, I take something with negative determinant, and then I take the identity everywhere else. And that ensures that if you picked an open set that was contained in the connected component of the identity, I've got something that can get me to the other side, so now I can generate everything. So that suffices. Hamilton's quaternions are connected, so any open set generates the whole thing, so you can just take the identity there. That's fantastic. And I'm gonna skip the algebra, the division algebra over local field, but you can do it, I swear. And so that should be a non. And basically, you can take sort of elements that look like this, and that's going to suffice. Because basically, what this is going to allow you to do, you can think about this as saying that I can now transform this matrix to something diagonal. Now you take an open subgroup near the identity, and that's going to contain sort of a pi, these elements that look like sort of diagonal matrices, pi v inverse or something, to some power, right? You're going to get some power of the uniformizer in that subgroup. So then once you get this, you take powers of this matrix, you can do it all. And so it's a little thought exercise, but and just a note for now, we've got these norms on all these algebras that we need to sort of control to get this height bound, and it's all bounded by the square root of the biggest prime in the set. You can just sort of work that by hand. And then, yeah, so the topological generator stuff, it's something you need to handle. But fortunately, they're not going to have too much effect on the height. You go do a little dirty work and you find your good topological generating set and you hold on to it, but it's really not going to affect this height bound. Because the point is, we have this lemma that says that this d sub s star is now generated by d sub s intersected with my fundamental domain. I forgot the x of c, right? It was x of c. Okay. Times a topological generator times the inverse of an element of f sub x. And so basically now what do you want to say? Okay, this set could be horrible to compute. But if I could show that everything in this set has bounded height, you see now I've made the problem easier. Because all I need to do is compute the things of bounded height, and those generators are a subset. And, well, if I've thrown in extra generators, okay, so fine, so be it. It's a way easier problem. Because now what am I doing? The things of bounded height, those are a lattice in some vector space. So now I just need to enumerate the lattice points of norm less than something. Now, of course, if you want to do that in the nose, that's a hard problem too. But basically, once you introduce a little bit of overkill, you can really just pop these generators out. And I'll show you an example, but this is about it. And so that's sort of where Ted stopped. I've gone through a few more details just in this example. And so in the quaternion algebra case, there's your height bound. It looks like that, if I copied correctly from the paper. So what is S? I've got this 1/2 to the S. S is the number of ramified places at infinity. So the number of places. So this, in our case, remember, we're looking at a quaternion algebra of a cube. So that's either 0 or 1. This M sub SF, well, that's the maximum finite prime in my set. And there you go. So that's fantastic. Like I said, this is highly computable, and once all these things are fairly small, it's actually quite easy to get ahead. So let's say a little bit about the idea of the proof. I'm not going to go through the details because I'll probably get confused too. So what do we want to do? We want to look at an element. So gamma is going to be an element of the S units. It's going to be one of these generators. And it's going to look like that. I'm not going to read all of that. You can read it faster than I can say it. So the X alpha and the Y beta are in my fundamental domain. Note the inverses on the Y and the beta. And then the thing in the middle of the sandwich is from the topological generating set. Okay. Now I want to show that that has a bounded height. Okay, so first let me, just for a little bit of ease, the W of gamma. That's going to be the set of places. Now note they have to all be in S because this thing is invertible outside S. Such that this norm is, oh, I want a strictly greater than 1. And crossing it out just makes it look more like a strict. Because those are all the places that contribute to the height. Remember, a height is a maximum of 1 and a valuation at a place. So these are the places that are contributing to the height of gamma. And so I can just write it out like this. So the height, by definition, looks like that, because it's 1 at every other place of Q. And now you do a little trick. You rearrange it. And this trick was really the insight of Lenstra that we can still push through with some consternation, but not a whole lot of consternation. You look at it like so. I haven't really done that much. So what did I do? I took, essentially I took my XZY inverse and turned it into an XZ det. You should think about it as sort of being the reduced norm. And I did that at this place, and I put the det inverses over here. And then the point is, this is particularly nice in, let's think about the quaternion algebra case. So the point is, I'm now going to be able to, so X comes from that convex symmetric set, so it's small. Z, that's topological generator, that was small by sort of construction. And now I want to show that this sort of det V YV times Y inverse is also small. But, you know, if you think about that det V is the reduced norm. And if we're in a quaternion algebra, let's say, you've got that is equal to YY bar. And you've got that Y inverse is equal to Y bar over the reduced norm. So the reduced norms cancel, and that det V YV times YV inverse just becomes YV bar. So now that's still an element. So now that becomes an element of X sub C again. That becomes an element of my convex symmetric set. Because I chose mine to be invariant under quaternion conjugation. But anyway, so the point is, that's small too. So really now you've just got to go in and analyze these pieces. And similar arguments happening on the non-Archimedean side. Okay? So you sort of build this to win, and that was Lenstra's beautiful idea. Yes. Yes. More to the center. Oh, yes, indeed. Better? Oh, sorry. Yeah, I'm all over the place. It's hard. I barely. Um, okay. So yeah, you study and bound each term, and the details. I'd rather do an example than two details. So this is my favorite algebra overview. Well, one of them. We've seen this a million times already, I guess. I know that the places where this remains division are the infinite place, where it becomes Hamilton's quaternions, and over the two adducts, this is still a division algebra. And I'm taking a suggestion from last night. So alpha is going to be 1 plus I plus j plus ij over 2. And so my order is going to be that sucker, the generated, 1, ij, and alpha. That's the Hurwitz order. And its discriminant is 2. And so if you think about it, that lattice, if you just considered it inside of R4, it has volume 1/2. But we're Hamilton's quaternions, so we take 4 times the usual measure. So we get 4 times 1/2, which is 2, which is the correct answer. So our set X sub C is going to be the things of, remember, it was the square norm that ended up being what we want to bound. So we get that the X sub C is the set of things with Euclidean length less than square root of C. Because our reduced norm is the square root. And so there's the volume. So you compute it, and there's C, 4 over pi. So we take x sub 4 over pi, and we're good for Minkowski. And you compute the mx, and it's just the square of that. Okay. So one thing I'd like to know is that these are very small. They're less than 2. That's going to be important. Because our assumption to make our machine work was that S contained all the rational primes such that P squared was less than M sub X. So that means that P is less than 4 over pi, which is less than 2. Which means that we can just take the infinite places. We don't even need to invert anything in this case. So we can find generators for just the unit group. In fact, this happens in some other small examples too. So, the theorem tells you you have to invert some primes, and if our constants were horrible, maybe you would always have to invert a bunch of primes. But actually, you do. This is sort of the reason why you have to get so technical. You boil it down, and you can actually really get your hands on this stuff. And then you compute the height bound by, we had those 4 terms, the product of 4 things. You just go through each one, and you get the height bound is 2.63. Great. And you do a short little computation, and you get the d star. Well, so the elements that you get from the computation are those, but sort of classically know that that's d star on the nose. So we're finding a generating set for d star by finding d star. Okay, great. That's the binary tetrahedral group. Sort of classical fact, which I don't know who this goes back to, but the binary tetrahedral group is the unit group of the quaternions over Q. And so you do our computation, and you just get everything. Well, okay. Fantastic. Now, of course, we only have to assume that it contains certain primes, that certain set being empty. So we can look instead now at some actual S units. We can just keep going. Like once you have the sort of necessary set of primes, you're off and running. You can throw in whatever else you want, and the method still works. So the height bound. Now there is a little bit of a contribution now from. Oh, it's what happened to our rock? I somehow must have flailed and hit the lock. So the height bound changes a little bit because there is a contribution. Remember, I had to take the maximum norm of a place. So as your places grow, the height bound is going to grow. But in this case, only by the largest prime to the 3 half. You go in your closet and have a cry and work at it for a while, and you can figure that out. So that's about 13. That's not so bad. Because what does that mean? The things satisfying that bound actually lie in 1/9 times d, right? Because you want the norm to be bound by 1/9. So you only need to consider things that look like this. Remember, alpha was that 1 plus I plus j plus ij over 2, the other generator for this order, where those are integral and 0 is less than or equal to n less than 2. And then you want the norm at the infinite place to be bounded by that, right? You want because you need the height to be bounded. So if you want to have a small, if you want to take a 1/9, then you've got to have your, you've got to have Archimedean norm 1, right? Because you'd have 9 times the Archimedean side to play with. You got to keep the non-Archimedeans and the Archimedean small. And so yeah, so you can just go to Mathematica and it'll compute them in about 5 seconds. You can just list them out. It just does it. It's quite incredible. You can be a little bit more efficient using the Brouhat history, but so you can sort of use a bit of geometry and use some related but slightly different methods and be a little clever and get generators. But it's only slightly more. You get, I think, like 42 generators out of this. I forgot, but it's not so bad. Something you can. I mean, what's the goal now? You've got this way to present things when they're acting on something geometrically. This it's in Sayre's book on trees, and it's originally, I have to correct Ted here. It's not due to Sayre, it's due to Macbeth, and he's my academic great grandfather, so I have to correct that. So so Macbeth sort of gave Macbeth, if you read it like an American, gave a way. Once you get these generators, you have this nice geometric action. You can come to a presentation. And as far as something with 42 generators, that's something a computer can handle pretty easily. That's pretty fantastic. So hopefully I've convinced you that this is not just total nonsense and you can actually go out and compute. And I'll just sort of state this for the record. So what if you wanted to take some other s with bigger primes? You end up with a height bound that is 256 over pi to the 4th times the largest prime to the 3 halves. And you can show that this unit group is generated. Now remember, the primes sit inside, right? Because z sits inside the order and all this stuff. So you get the primes inside, and the things whose norms lie in that set, inside the actual integral points. That's kind of fantastic. You have to do a little more work to get it down to the set, but excuse me. Sorry, out on the internet, I think I just coughed right into you. Yeah, sure. Yeah. All right. Yeah. All right. That's where I had it before. Oh, sorry, I don't know left from right. Okay, now I want to spend the rest of my time talking about a potential application that Ted brought up, which is the congruent subgroup property, and doing some experimentation. Because, first of all, we're essentially, our results are directly addressing finding generators for cases where this problem is most wide open. And to sort of motivate this problem to number theorists, it's really telling you when you have a sort of arithmetic group, how much does the number theory see of this group? The congruent subgroup property asks, does it see all of it? And I'll make that more precise in the next few sheets of paper. But basically, we're getting access to presentations for the places where this problem is the most wide open. And the simplest is case where it's most wide open. So I'll start with an example. And this goes back to the 1880s. So PSL2Z, the modular group, you can think about that as a free product of an element of order 2, right, and an element of order 3, the sort of classical generators. Now this group has lots of finite index subgroups. What do I mean by that? Well, so here's a particularly nice family that our number theorists should care about. You take the kernel of a reduction homomorphism. It's a so-called congruent subgroup. And I can take pullbacks of subgroups of PSL2. Those are nice finite index subgroups too. And they all contain those kernels. Okay, so these are the congruent subgroups. And the question is, well, is that everything? And so this is a more precise version of my saying, does the number theory see everything? Right? So these are sort of nice finite index subgroups, or you could say finite covers of the modular curve. And these are probably the most important covers of the modular curve, in a sense. And you could ask, is this everything? So is studying these subgroups enough to see all? Well, the answer is no. And this was noticed by various people. I think Poincaré, for instance, in the late 1800s. And, well, A5 is generated by elements of order 2 and order 3, so there's a homomorphism. That's freely generated by elements of order 2 and 3, so we just build a homomorphism by hand by sort of first-year graduate algebra. But the fact is that A5 is never a subgroup of one of these. It's simple, so it would have to lie in a factor, so you really just have to look at PSL2 over finite fields, and you can show that A5 is never in there. So this never comes as a pullback of a subgroup of PSL2. And so there you go. There's a non-congruent subgroup. So congruent subgroup property fails. And, there's an impression that sort of nobody considered it's like, okay, well, that's false. And people didn't really think about it until much later. Ends up it's a quite interesting problem. So, of course, I got my arrows going the wrong way the first time. But for the experts, I'll be a little fancy. So if you have an algebraic group over some ring, you can think about the profinite completion of the R points going to G of the profinite completion of R. So here, what am I saying? The profinite completion of PSL2Z going to the PSL2 of the profinite completion of Z, that's just the product of all the PSL2 ZPs. This is a fancier version. So you can ask, does this have a kernel? And what is this saying? This is saying, are there finite quotients of PSL2Z that are not coming from the sort of natural congruence quotients? And in fact, for SLNZ for n greater than or equal to 3, the answer is yes. And this was done by a bunch of people. Bass Milner Serre is the sort of canonical paper, but there's a lot of work about this in the 60s. There's people working on K-theory, and they sort of, Bass Milner and Serre ended up in the same room at the same time, and then an IHES paper just had to happen. And so that's telling you that, jeez. Bring out the big one, yeah. The camera's just the camera just really likes this theorem. It's trying to get close and really understand what's going on here. So that's saying that if you think about this sort of locally symmetric space, it's telling you that number theory really tells you all the geometry of the coverings of this. So that's really fantastic. So n equals 2, bad or good, depending on your disposition, I guess. N equals 3, good or bad. So there's been a lot of work on this problem by people algebraic groups. So I want to sort of come back to motivate the example we've been talking about. So Sayre also considered SL2O sub S, where you're looking at the ring of integers as a number field. And so we already saw in the case k equals q that this is false. So is it going to be false for all SL2s? You could say, well, SL2 is rank 1 and blah, blah, blah. But in fact, Sayre showed this has the congruent subgroup property even only if S has at least 2 things in it. And you have to have all the Archimedean places. You're forced to. So the things that don't, so how could you have the size of S be 1 if you have to have all the Archimedean places? Well, you could be Q or you could be an imaginary quadratic field. And these correspond to lattices in SL2R and SL2C. And they have free quotients, and they just have so many finite X subgroups, they're just spilling out their pockets. But SL2Z adjoin 1 over P, now S has cardinality 2, that has the congruent subgroup property. And so does SL2Z adjoin root D. And I should have, 1 plus root D over 2 in certain cases, but I was too lazy, so forgive me. So these Hilbert modular groups, which are well studied as well, those do have this congruent subgroup property. So Sayre sort of just killed the question in this case. And you might say, so what's the next thing you might look at after SL2? Well, you'd look at forms of SL2, which would be quaternion algebras. And that's sort of the thing with which I would like to finish. Okay, so I've got some quaternion algebra over a number field. I've got some set S containing all my Archimedean places. And if I assume that B is ramified at all but one place, then the congruent subgroup property failed. Now again, what's the reason here? The point is that you're getting, again, lattices in SL2R and SL2C. And it's, well, if you have a lattice in SL2R, you're thinking about perhaps, these curves just have tons of covers. They've got free quotients, and you can just build too many covers to be congruent. SL2C, it's a little more subtle that those can't have the congruent subgroup property. It's a beautiful argument due to Blavatsky that uses the Golod-Shafarevich inequality. It's a really, really beautiful argument. And if you actually care, you can ask me later and I'll tell you because it's just great. If you assume B is ramified everywhere, so there's one setting where we know. Good, done. Here's another setting where we know. If B ramifies everywhere, so it's Hamilton's quaternions everywhere, and you throw in just one other place, then it fails. Because you get a lattice in SL2, well, I guess it might be if KP isn't QP. I should have said SL2 KP, not QP, sorry. You get a lattice in SL2 QP. Now what does that mean? That means something acting discretely on a tree. And a little basic algebraic topology tells you that that has a free subgroup of finite index. So it can't have this congruent subgroup property. And this is a virtually free group. That's theorem of Hauer. And that's it. Those are the two cases. That's all we know. So Sayre totally killed SL2 over number field. But in these quaternion algebra cases, in a sense, sort of number theoretically, perhaps these are the next easiest case. You just know nothing. That's just ridiculous. And so I'd like to note that those cases are, so Sayre told you that S had to have size 1 to have the congruent subgroup property. So these are the cases where S minus the set of ramified branches at infinity is equal to 1. So that begs the question. It leads to an interesting, perhaps, conjecture that if that number is greater than or equal to 2, it does. But so that's one of the things that we hope we could sort of experiment with, is to get presentations for these groups. Look at the finite quotients. Is there an A5 quotient? since the algebraic groups people have no ideas, maybe well they have ideas, they just haven't proven it. I don't. They might see this on the internet and then send me angry emails. I know you have ideas, fellas and ladies. So what I want to finish with is another little fact. I'm going to do a computer experiment to show that what Ted and I have done actually gives you computable sort of things. So I've got 5 minutes, so this is great. So I'll be a little fancy, so if you don't like this stuff, just turn it off. So I've got some algebraic semi-simple group over Q. I'm taking the z points of this group scheme, and suppose that I have a homomorphism onto the integers. Now, if you think about sort of, Riemann surfaces, those have homomorphisms. Their fundamental groups have these homomorphisms, and CSP fails. What's the point? CSP tells you that, well, really, you should say that the kernel's finite, but it says that the profinite completion and the profinite completion of G of the profinite completion is isomorphic to the profinite completion of G. But you see, if you had a map on a Z, you get a map to Z hat. And this is a product of things that don't map onto it. And so that tells you that this has a huge kernel. So basically, one way to show that the congruent subgroup property fails, and there are a lot of reasons where sometimes you can't use this trick, but here's a trick that works. If you can find non-trivial cohomology in dimension 1, that's what I'm saying here. If you can find an abelian, an infinite cyclic quotient of your group, then you're done. And so what I'd like to finish with is an example that sort of exploits this to show that a known example does not have the congruent subgroup property. So what I'm going to do, I'm actually just going to hold my laptop up here like this. And see, that's perfect. We could have spent like 4 hours trying to hook this thing up correctly, but we'll just do this. So this is Magma. Magma does computer algebra all the time. It's great. I should probably be using Sage because it's free. But so the very bottom 2 lines. G is group ABC such that A squared, B cubed, C squared, AB cubed, and B and C commute. That's what the bracket there means. So so Ted and I have not checked this rigorously, but we're pretty sure that this is a presentation for D sub S star, where D is the Hurwitz order. So back to the case, the example I worked. So infinity 3. So this should be a presentation for the infinity 3 group for this order in quaternions over Q. So the 3 units should be that group. It's basically done. So one thing to notice, so A and B, those are D star. That's the binary tetrahedral. What's the presentation of the binary tetrahedral group? It's A squared, B cubed, AB cubed. Right? It's A4. I've killed scalars. Oh, I'm so mean. I'm actually lying. So it's not D star, it's D star mod scalars. Okay, sorry. Everything, I've killed the center. So I can do, once I get a presentation for one of these S-arithmetic groups, I can go to Magma and say, well, why don't you just tell me some normal subgroups? You can look for regular subgroups too, but I'm going to look for low index normal subgroups, and I'm going to 366. Why am I going to 366? The size of PGL2F7, which happens to be a congruence quotient. And there you go, done. The computer did that quickly. So now you can, I'm going to have to type if H Abelian quotient H. I need to access the group because there's also a homomorphism there. And that should have been 4. So all of those groups have free abelian quotient. Not the congruent subgroup. And you can check the indices of these. I'm not going to do it. But in fact, those are all congruents. But anyway, they're free groups. You can actually compute that those are actually free groups on 9, 11, 17, 29, and 31 generators. So you've got free subgroups of finite index in this group. So yeah, so I hope what I've convinced you over the past 47 minutes is that this method that Ted and I have been developing actually has some computational teeth, from which you might actually be able to get some sort of experimental evidence and perhaps some very nice examples of S-unit groups that people just don't understand at all. I mean, so there is not a known, to my knowledge, there's not a known presentation for an S-arithmetic lattice in a semi-simple Lie group where the size of S is greater than or equal to 2, and contains a non-Archimedean place. Okay. You have to be a little technical. So this should be a way that one could actually just give a computer a very small number of things and actually compute some presentations for things that have been sort of basically inaccessible. And the key is that we get this fundamental domain. And producing a fundamental domain is hard, and that's sort of the beauty. And that we can do it effectively is just splendid. And so yeah, we hope this is useful.